FloEFD Quick Tips video. For this FloEFD Quick Tips video, we'll be looking at the combustion modeling capabilities of FloEFD. Combustion modeling in FloEFD is part of the Advanced module, which is an add-on functionality module. A datasheet outlining the exact capabilities of the Advanced module can be found online. Some of the details for combustion modeling can be seen here, such as the ideal gas requirement and fuels and oxidizers available. Users create their own mixtures from a range of predefined materials in the combustion library. The benefits of combustion modeling are that the flame shape can be determined and optimized. Combustion products can be determined for emissions regulations, and the overall burner efficiency can be analyzed. There are two models for burning. These are equilibrium, which assumes instant mixture ignition on contact. This is a steady state analysis. The other is limited combustion rate, in which the fuel and oxidizer are mixed and then ignited with a heat source. This is a transient simulation and the one we'll be looking at today. For this demonstration of the combustion capabilities of FloEFD, we'll be using a domestic burner ring which uses methane for fuel. There is an inner and outer ring and an additional igniter part which we'll cover later. This analysis will be performed in two steps: the cold mixing in steady state and the transient burning phase. The computational domain size for the mixing analysis can be seen here. The cross-section through the burner shows the gas inlet on the left, the nozzle for generating a high-velocity jet, and the mixing chamber. Air is drawn in and mixed due to the Venturi effect. Methane is supplied at 200 pascals above atmospheric pressure. The substance concentrations option shows that this is 100% fuel from this inlet. The project fluid is a predefined methane and air combination, although other admixtures can be defined. Looking at the results of the mixing, we can see the pressure here with the higher methane supply pressure. A high velocity zone around the nozzle can be seen where the cross-section is constricted, which creates the jet for drawing in the ambient air. Finally, looking at the mass fraction of fuel, we can see the mixing pattern and the resultant volatile mixture at the ring outlet. Probing allows determination of local fuel concentration. The flow trajectories show how the mixture is leaving the ring and what the pattern looks like. The whole purpose of this steady-state mixing analysis is to determine the flow rate of the mixture leaving the ring outlets and what the average fuel concentration is. This is determined by interrogating the surface goals on the outlet. We can see a total mass flow rate of 0.4467 kg per hour at 15.7 methane by mass. Now let's look at the burning step of the analysis. This time we are running the model as a transient, and we have the time-dependent option enabled in general settings along with gravity. The inlet mass flow boundary condition is taken from the previous simulation. As we are using the limited combustion rate option, we need an igniter to start the reaction. This is where this small sphere comes in. A volume source with a high temperature is defined to be on between 0.5 and 0.6 seconds. This is enough time to ignite the mixture. During the actual solver execution, we can preview flow parameters to ensure sensible results. Here we're looking at the burner from two perspectives showing temperature. The initial heat source in the center can be seen and the flame propagating outwards from this transiently. The solution stops once the flame has become steady state. Once solved, the results show a variety of combustion-related parameters. Temperature shows hotspots in the simulation. The hottest areas are around the gas outlets, which is expected. This plot gives us an idea of the flame pattern. The velocity shows around 1 meter per second around the burner due to the high temperature combustion gas moving against gravity. Combustion progress shows where the combustion is actually occurring, which is close to the outlets. We can also plot various combustion products such as CO2, CO, NOx, and residual fuel. This is useful for emissions determination. An ISO surface showing combustion at a constant temperature gives a clearer idea of the flame pattern. Flow trajectories show the path of the combustion gases. FloEFD can be used to optimize the mixing and burning of fuels and oxidizers, all within your MCAD system, to determine the product performance before prototyping. This has been another 5-minute FloEFD quick tips video from Mentor Graphics. Please look out for our other videos.